Hello. So in this video, we're going to look through Haberman's section 2.3, where kind of the physical problem that we'll be looking at is starting to solve the heat equation with prescribed temperature at both endpoints, where we have a finite or kind of a rod with some fixed length. That's the physical setup. In practice, what we're going to be doing is introducing kind of the fundamental tool that we'll be using throughout the rest of this course to solve the heat equation and some of these other PDEs. And kind of the starting point for that tool is this technique called separation of variables, where kind of in short, we look for solutions to the heat equation, which are composed of a product of a function just depending on the spatial variable and a function just depending on the time variable. Okay, so what are we going to be doing in this video? Well, first of all, we're going to set up the problem and say kind of and quantify kind of what the actual mathematical problem we're interested in is. After which we'll introduce the main technique, which is called separation of variables. As I mentioned, separation of variables, we seek solutions that are composed of a product of a function that just depends on x and a function that just depends on t. Okay, and so in the process, we'll end up with kind of two subproblems. One is going to be what I'm calling this time-dependent piece. The other is what I'm calling this space-dependent piece, or a little more generally is kind of often referred to as an eigenvalue problem. Okay. But yeah, so separation of variables will lead to these two kind of subproblems. We'll solve each of these subproblems. That'll give us what we're calling a product solution for the heat equation. And then we'll use this principle of superposition to add together a bunch of these solutions to construct new solutions. And yeah, so these solutions will work for the PDE and the boundary conditions that we're going to give. They don't a priori work for the initial condition that we may have in the problem. And so the question is, well, how do we match this general solution that we get from superposition? How do we match it to the initial condition? Okay? And so we have kind of ways of computing, say, coefficients that will make that matching work out. And so underlying kind of how this computation goes is this notion of orthogonality of functions, and in particular sine functions. Okay? And so if you recall from linear algebra, right, orthogonality refers to kind of a notion of two vectors being perpendicular. Okay? And so in our context, the vectors that we're working with are functions. And so question is, do we have a collection of functions that are perpendicular to one another or are orthogonal to one another? And sines do work out in this way. Okay, so once we've talked about that a little bit, then we'll look at an example of, say, a more natural kind of heat equation problem with a more natural initial condition. We'll use everything we've set up to solve that. And then we'll summarize kind of everything that was talked about here. Okay. So let's get started. So, right, what is the problem setup? What is the actual, quantification of kind of this heat equation that we're interested in here? So the problem we'll focus on is the following. So we have the heat equation, right, where kind of from how it's written, we're assuming that kind of these properties of the rod, like the mass density, specific heat, and then the this flux coefficient, right, K naught, those are all constant. Those are collected in this little k. And moreover, we're assuming that there isn't a source term, right? Say Q is equal to 0. Okay, so this is the PDE we're interested in. The kind of range of parameters or kind of domain of these variables that we'll care about are Well, X is going to go from 0 to L. Okay, so 0 is the left end of the rod, L is the right end of the rod. And we're interested in what happens for positive time. T equals 0 is kind of our initial condition. The initial temperature distribution as T goes off to infinity, that'll kind of show us how heat distributes and heat behaves, at least for this setup. Okay. Cool. So this is the PDE and the geometry that we're interested in. The kind of how this problem was stated was, we're interested in describing 0 temperature at the endpoints. Okay. So what does that look like? Well, the value of the temperature at X equals 0, which is the left endpoint, that's going to be 0. The value of the temperature at the right endpoint, which is at X equals L, that's also going to be 0. And then this should hold true for all time, right? So no matter what T gets plugged in, T positive, these hold true. And then finally, we're going to specify an initial condition that says, here's what the initial temperature profile is. And that's just going to be some function f of x. Okay. And so one note is that, well, so here, and then here, we have strict inequalities, right? So we're not saying, x equals 0 and x equals L. In practice, the value of kind of f and some of these other things at a specific, t equals 0 or x equals 0, in practice, they don't matter too much. I should clarify. So the value of f at x equals 0 and x equals L in practice doesn't really matter. And we'll kind of see why in a bit. But anyway, so this is a problem that we're focusing on. Okay, heat equation, 0 boundary conditions, and this is our initial condition. Okay. So let's get started with why we're actually here. So the technique that we'll be developing in this video is called separation variables. So what does this technique entail? So as the name implies, we want to separate the variables. And so what we're going to do is we're going to look for solutions u of x comma t that take this form, right? So our solution u of xt, it's a product of two functions. Okay. One of the functions just depends on x, the other function just depends on g. Okay. So if we want to start to get at, figuring out what phi and g must be to solve this equation, right? Well, let's plug it into the PDE. And so recall the original PDE, or the PDE that we're interested in right now, is du dt, okay, d squared u dx squared. Okay, so in particular, we have a time derivative for u, and we have two spatial derivatives for u. Okay, so what we're going to have to do is, if we want to plug in the separated solution into the PDE, let's compute some derivatives. So time derivative, phi doesn't depend on time, so it's a constant with respect to time. So this time derivative only affects g. Likewise, g is constant with respect to x. So when we take an x derivative, it only affects phi and not g. And then if we take another x derivative, it only affects phi and not g. Okay, so these are the derivatives of u with respect to x and t, written out in terms of phi and g. Okay, and so now what we can do is go ahead and just plug in these pieces for those derivatives in the original PDE. And this is what we're going to end up with. Okay. Okay. And so now what we're going to do is we're going to collect all of the kind of x dependent pieces on one side and all of the g dependent pieces on the other side. And moreover, we're going to, just for convenience sake, we're going to take this k and move it over to the g side. So if you divide by phi, that's going to go down there. If you divide by kg, that's going to go down there. And so we end up with this expression. Okay. Cool. So an important thing to note is that, right, so g is just a function of t, right? G does not depend on x. So everything on the side is just a function of t. Likewise, phi only depends on x. And so then hence b squared phi dx squared only depends on x. So everything on this side only depends on x. Right, so this side only depends on t. This side only depends on x. Okay. And so the question is, well, what happens if we vary one of these variables, right? So for example, if we change the value of t, okay, sure, a priori, this side is going to change, okay? G depends on t, dg dt depends on t. So vary t, a priori, the value over here is going to change, okay? But over on this side, nothing over here depends on t. So as we vary t, this side doesn't change, okay? So because this side doesn't change and we have an equality, this side doesn't change at all. Okay? So that tells us that this quantity right here is actually constant with respect to t as well, just as this side is constant with respect to t. And you can flip the sides, do the same analysis, right? Vary x. A priori, this is a function of x. This is a function of x. So if we vary x, this whole thing is going to change. Okay. But this side doesn't depend on x. So as we vary x, this side remains constant. And since we have an equality, whatever this constant is should also be the constant here. Okay. So both sides are constant with respect to x and t, which tells us that, right, yeah, both sides are a constant. Okay. And so that's a fact that we're going to exploit next to start figuring out what g and phi could possibly be. Right, so, right, as we argued, right, each side of this is constant, okay? And so we're going to call that common constant minus lambda, okay? We don't yet know what lambda is. Presumably lambda is a real number. That minus sign we're going to include for convenience, okay? But otherwise we don't yet know what lambda is. Okay, all we know is that each side of this equation right here, each side is equal to the same constant. Okay, so what we've written here actually has kind of two equations hidden within it, right? This thing is equal to minus lambda, just as this thing is equal to minus lambda. So writing that out explicitly, we're going to get these two ODEs, and then we can take it a step further, move the kg to the other side. So then this becomes dg dt is equal to minus lambda kg. Same thing down here, move this phi to the other side. We're going to get d squared phi dx squared is minus lambda phi. Okay. Okay, and so what we're going to be doing next is essentially, right, solving each of these ODEs and then trying to figure out what possibilities there are for lambda. Okay, so up to here, right, all we've done is worked just with the PDE, right? We've plugged in the separated solution and we said, okay, well, if we have a separated solution, here's what the PDE becomes. We have these two ODEs, great. But when we set up the problem, right, we had two more pieces of information. We had boundary conditions in X, and then we also had an initial condition in T. Okay. So what we're going to do now is we're actually going to ignore the initial condition. We're going to come back to that in a bit. And now what we're going to do is we're going to try to figure out what these boundary conditions look like in terms of our separated solution, right? U of xt is equal to phi of x, g of t. Okay. Okay. So, right, how do these boundary conditions look for our separated solution? U of xt is equal to phi of x, g of t. Well, if we look at the first one, u of 0 comma t is equal to 0. Note that this is true for any possible value of t that we plug in. So u of 0 comma t, that implies that, well, plug in x equals 0 to this. You just get an x equals 0. We're not plugging in t, so we still have g of t. U of 0 comma t implies phi of 0 times g of t is equal to 0. Okay, so we have a product of two things is equal to 0. That tells us that either phi of 0 is equal to 0 or g of t is equal to 0. Okay, so let's look at this possibility first. Can it happen? Well, if g of t is equal to 0, right, this has to hold for every possible t. So g of t is 0 for every possible t. That tells us that the separated solution, right, which is that, plug in g of t is equal to 0, becomes that, which is equal to 0, right? So if g of t is 0, then our separated solution is identically 0. Doesn't matter what you plug in, it's going to be 0. We call these trivial solutions, right? Because in a sense, they trivially satisfy the heat equation because on each side of the equation, you just get 0. Right, and so if you're just looking at the PDE and the boundary conditions, sure, it's a trivial solution, it works. It's not very interesting, just because it's not really doing anything. And so in part because of that, because it's not really doing anything, we're going to not really care about these solutions. Right, but I'd said, well, let's ignore the initial condition for now. Okay. If you actually take a look at the initial condition, then generally this won't satisfy the initial condition. So that may be another reason to ignore trivial solutions. Okay? Whichever reason you're more comfortable with, we're not going to account for these trivial solutions. We're not going to deal with them. So we're going to say, well, if g of t was 0, we get a trivial solution. We don't want that. So we're going to say g of t cannot be 0, at least coming from this condition. Okay. So the only other possibility from here is that, well, phi of 0 is equal to 0. Okay. And you can do the same sort of analysis to show that, well, right, plug in L for x. So L right there, that's going to be equal to 0. That's going to tell you that phi of L times g of t is equal to 0. Do the same exact analysis. You're going to conclude that you must have phi of L is equal to 0. Okay. All right, so the takeaway here is that these two conditions right here, these imply that phi of 0 is 0, and then phi of L is equal to 0. Okay. Cool. So great. So what we've done is we said, well, if we have a separated solution, we have these two ODEs. For the second ODE, we also have phi of 0 is phi of L, which is equal to 0. Okay. And so now what we're going to do is we're going to draw on our experience from solving ODEs and actually solve each of these kind of equations. Okay. So we're going to start with the time-dependent piece. We're going to get a sense of what lambda probably should be, what this thing looks like in general, etc. And then we're going to revisit the spatial piece. And then from the spatial piece, we'll be able to say what possibilities there are for lambda. Okay. Cool. Okay, so let's start solving things. So time-dependent piece. Right. This is one way of writing what we had. Another way of writing it was dg dt is equal to minus lambda k g. Okay. Another way of writing this, right, getting towards actually kind of integrating and solving these ODEs, we can write this as dg over g is equal to minus lambda k dt, right? Sure, we're kind of treating these infinitesimals as fractions, which maybe is less or a little more frowned upon, but actually for actually solving things, it doesn't really matter. Okay, so this expression right here is what appears down here. Okay, so let's actually solve this, right? So what does this look like? Well, if you integrate both sides, or if you want to be a little more kind of formal about it, let's find an antiderivative for each side. Okay. On the left-hand side, an antiderivative is log of g, right? Because take a derivative of g, you're going to get 1 over g times an infinitesimal dg. That's exactly this. On the right-hand side, an antiderivative for this is going to be minus k lambda t, or minus lambda kt, whatever order you want to put them in. Okay, because differentiate this, you get this. Right, but when we're finding antiderivatives for kind of functions and equations, right, we only know antiderivatives up to a constant, right? Because change the constant, or take a derivative, constant goes to 0, so you don't see that in that differentiated version. So going from here to here, we're going to have some unknown constant. Okay, and in this case, we're going to keep this unknown constant with the time piece. Great. So now what we're going to do, let's solve for g, right? Exponentiate both sides. So writing it out explicitly, you're going to get e to the ln of g is equal to e to the minus lambda k t plus c. E to the log, right? They're inverse functions of one another. So on the left, you get g of t. On the right, you can rewrite this as e to the minus lambda k t times e to the c, right? Because e to the whatever plus whatever is e to the whatever times e to the other whatever. Okay, and so then the observation is, well, this thing right here, this is just some constant. Okay, so this we're going to rename just as our arbitrary constant here. Okay, and then that gets us this final expression for g of t, right? So for this time-dependent piece, again, we don't know what this constant lambda is, okay? But for solving for g, it doesn't really matter. Whatever lambda is, whatever that constant lambda is, g of t has to be this function. This is the solution. Okay. Okay. So we're not going to know lambda just from studying this time-dependent piece, but we can get a sense of what lambda probably should be, or at least what the sign of lambda should be. So what we're going to do is we're going to ask, well, for a separated solution, I'll write again, u of xt, phi of x, g of t. Question is, what happens as time goes to infinity, right? So we let the system evolve for a really long time. Well, depending on the sign of lambda, okay, we're going to get a different behavior for g of t. Okay. Okay, so, right, if lambda is negative, so assuming that k is positive, t is going to be positive in our setup. If lambda is negative, then this term minus k lambda t, that's going to be positive, right? And so then what we're looking at is essentially the function e to the rt with r greater than 0. So here, r is going to be minus lambda k. Okay? And if we plot this function where r is a parameter, it's going to look like that. Right? So as t goes to infinity, our solution will kind of be unbounded. It'll tend to infinity. Okay, and so already here, we might be thinking, well, maybe physically that doesn't make a lot of sense, right? So if lambda is negative, what this is saying is that, right, our time-dependent piece is just going to blow up, okay? And so this is going to infinity. And so unless phi is identically 0, right, if phi is non-zero anywhere between 0 and L, then fix that point, x, let t go to infinity, g of t is going to go into infinity, so then the temperature is going to go to infinity as well. Okay. Right, so if lambda appearing this constant is negative, then the solution that we get doesn't seem to be physically reasonable. Okay. And so this is already suggesting that, well, maybe maybe lambda appearing in the constant, maybe lambda should not be negative. Maybe it'll have to be positive. Okay. Okay, and so, right, what happens if we keep kind of looking at these cases? Well, if lambda's positive, minus lambda kt, right? So kt and lambda are all positive. Throw in a minus sign, everything's going to be negative. So then we're looking at e to the rt with r negative. And this looks like something like that. So as t goes to infinity, our solution will go to 0. Okay. And maybe for, right, heat equation, one-dimensional rod, 0 temperature at each endpoint, maybe this makes a whole lot more sense, right? Because if you say, well, let the system evolve, at 2 specific points, temperature is going to be 0, right? Heat wants to flow from high temperature to low temperature. So even if the initial temperature distribution is all positive, right, heat will keep flowing to these 0 temperature endpoints. And so kind of this temperature distribution, the solution to this heat equation, that'll keep getting pushed down to 0. And so maybe this is the behavior that we expect to see. Okay. And so maybe the lambda that appears in this constant minus lambda, that should probably be positive. Okay. So this is something that we're going to be looking for and checking for when we incorporate the boundary conditions and solve that spatial piece. Okay. Finally, you can also look, well, you had positive lambda, you had negative lambda. What happens if lambda is 0? Right. Well, if lambda is 0, minus lambda kt is equal to 0. And so this term, this exponential will be e to the 0, which is equal to 1. Okay. And so then in this case, this is saying that, well, the time piece g of t, this is just 1. And so that might correspond to something like an equilibrium solution, which you have heat equation with no source and 0 temperature. At the endpoints, your equilibrium temperature should be 0. And so in that case, you might expect that phi of x is going to be 0. But yeah, so anyways, takeaway here is this is probably what we expect to happen, and we'll actually see that this is what happens later on. And so I should clarify, so this bit right here should actually read, we hope that the only admissible lambda are lambda positive. I guess technically lambda equals 0 doesn't give us any physical issues, but this is what we're going to be aiming for, lambda positive. Okay, cool. So that's the time-dependent piece essentially solved, right? This is the form of the solution. Sure, we have a constant we need to figure out. Sure, we have another constant lambda we need to figure out. But presumably those will be accounted for kind of in the next few steps. Okay, so now let's look at the spatial piece, the space-dependent piece. And these kinds of problems show up a lot, so much so that they have kind of a specific name, usually called eigenvalue problems. Right, and the connection to linear algebra isn't a coincidence. It's very much the same sort of behavior where you're applying an operator and you want to look for vectors that are essentially unchanged by this operator. They're just rescaled. Okay, so those are eigenvalue problems from linear algebra where you have a linear operator, right? AV is equal to lambda V, say. We're doing the same thing here, except the linear operator is going to be a differential operator. And then our vector v is going to be a function. Okay, so let's see that written out. Right, so recall, right, the spatial piece looked like this, where we can also write this as d squared phi dx squared is minus lambda phi. And here we want lambda positive, right, because that gave us physically reasonable solutions in the time piece. And then we also have these boundary conditions. Yeah, okay. So these are examples of eigenvalue problems where lambda is an unknown as well as phi. And so the question is, which pairs phi and lambda satisfy this, this equation? Okay, and so if you want to connect it to kind of the linear algebra perspective, you might write this as AV is equal to minus lambda V, where now A might be a matrix and V might be a vector, right? It's essentially the same kind of problem. It's just the specific objects we're plugging in, they look a little different. Okay, but the same kind of vocabulary is there. So eigenvalues are the values for lambda. Eigenfunctions are the actual solution functions phi. And in particular, we're going to also require that the phi that we kind of get, we want those phi to be non-trivial. Okay, because of course, say even in this formulation, right, if v is a zero vector, right, A applied to the zero vector is 0, lambda times the zero vector is a zero vector. So it solves it, but it doesn't really give us anything super interesting. So we're going to avoid the trivial solutions, and we're just going to look for non-trivial eigenfunctions phi. Okay. Okay. Okay, so how do we actually solve this? So what we're going to do, right, again, here's the ODE with the boundary conditions. What we're going to do is split the analysis into 3 cases. Okay, and so what'll turn out is that, so in each of these 3 cases, we can explicitly write out what phi looks like. And we can do that because of, we know how to solve constant coefficient ODEs. We know what the solutions look like. And so what we're going to do is we're going to split up kind of our analysis of what possible lambda there are into what if lambda is positive, what if lambda is negative, and what if lambda is equal to 0. And so punchline will be, so this is possible coming from, I mean, this is the intuition that we got from the time-dependent piece. And then it'll turn out that these 2 cases are not possible, at least for these boundary conditions. Okay, if you change the boundary conditions, you might have different possibilities. Generally, if you change the boundary conditions, you might have lambda equals 0 be viable. But for this problem right now, what we're going to do is look separately at lambda greater than 0, lambda less than 0, lambda equals 0. And in each case, we're going to show whether or not such functions phi actually exist. Okay, and so I've been saying, right, we can actually write out what the solutions look like in each of these cases. Okay, and so, right, kind of in general, if we have a second order ODE of this form, right, what we can do is say, assume y is equal to e to the r x. Okay, just look for solutions of this form. This implies that so e to the rx, if you write it out, you get r squared plus lambda equals 0. Right, two derivatives, you're going to have two r's come down, no derivatives, so no r's. So you're going to get this sort of thing. This implies r squared plus lambda is 0, which implies our solutions are going to look like e to the plus or minus square root minus lambda x. Okay. Yeah. And so in general, we're going to take linear combinations of those. And so now the interesting thing comes up, right? So if lambda is negative, minus lambda is positive, so we can take a square root without any issues, right? We're comfortable with that. If lambda is positive, minus lambda is negative, and so then, right, so if lambda is positive, then r is going to be plus or minus I square root lambda. So then our general solution is going to be something like C1 e to the I root lambda x plus C2 e to the minus I root lambda x. Okay, which is fine. I mean, it solves it, sure, but it doesn't really tell us much about what's actually happening. And then the observation is, well, we have this thing called Euler's identity, which says, well, if you have an expression of this form, e to the I theta, where theta is a real number, this you can write as cosine of theta plus I sine of theta. So then this whole thing, making that substitution, becomes, let's see, so this will be C1 plus C2 cosine of root lambda x. And then we're going to have plus I C1 minus C2 sine of root lambda x. Okay, so again, take this expression, plug it in there, plug it in there. Use the fact that cosine of minus theta is cosine of theta. Use the fact that sine of minus theta is minus sine of theta. You're going to get this. And then what we're going to do is we're going to say, well, let's rename these constants, because again, they're constants. We're going to get something like, maybe I'll call it C1 tilde, just a new C1 of cosine root lambda x plus a new C2 tilde sine root lambda x. Okay. So when lambda is positive, our roots are imaginary. We can still use these exponentials as their solutions, but because we have these imaginary things showing up, we can use Euler's identity to write our solution just in terms of cosine and sine. And so then determining what these constants are that'll come from other information that we're given in the problem, generally boundary conditions. Okay, but the point is that, right, depending on lambda, we know exactly what the solutions look like. And so technically what's missing is, so y is going to be c1 plus c2x when lambda is 0. So that's kind of the final case. But yeah. Okay. So now let's go through the analysis. Let's look at each case. Let's use these template solutions and then just see what's possible with lambda and phi. Okay, so for lambda positive, we know our solutions look like this. Okay, and so now the question is, well, for our solutions that look like this, what are possibilities for C1 and lambda? Okay. And so, as I mentioned, to do that, we plug in the boundary conditions. Okay. So we have two boundary conditions, right? Phi of 0 is equal to 0, phi of L is equal to 0. So if we use the first one, we'll plug in x equals 0, right? So x equals 0 there and there. Cosine of 0 is 1. Sine of 0 is 0. So what we end up with is C1 times 0 plus C2 times 1, and that's equal to 0 because, right, phi of 0 is equal to 0. So this whole thing is that, this is that. Okay. C1 times 0 is 0, so we end up with C2 is equal to 0. Okay. So already what that tells us is that for these boundary conditions, our eigenfunction phi can't have a cosine term. It's just going to have a sine term, which already is something interesting. Okay. So our solutions phi are just going to be C1, some constant times sine of root lambda x. Okay. And so now let's see what the other boundary condition gives us. Okay, so phi of L is equal to 0. Okay. Plug in x equals L right there. And again, we don't have to worry about this term. Okay, so phi of L is equal to 0 gives us, right, plug in L here. This thing is equal to 0. And so now either C1 is equal to 0 or sine of root lambda L is equal to 0. C1 can't be 0 because if C1 is equal to 0, then C1 and C2 are 0, right? Because we saw a second ago that C2 is equal to 0. And this gives us a trivial solution, which are the ones we want to avoid. Okay. So this tells us that C1 is non-zero. Okay, so this is non-zero. And so sine of root lambda L is equal to 0. Okay, and so then the question is, well, what does that tell us about root lambda L? So what we can do, draw a little plot here. So this is going to be sine of x. This is the x-axis. What are the zeros of sine? Well, we have a 0 there. It's 2 pi periodic, so this should be 2 pi. This value should be halfway through. Okay. So if sine of x is equal to 0, this tells us that x is going to be an integer multiple of pi, right? And so then that's exactly what's happening in here, right? So sine of root lambda L is equal to 0 tells us that this argument right here, root lambda L, has to be one of these multiples of pi. And so then that's what this condition is. We don't necessarily know which root it is. We don't necessarily know which n it is, but we know it's one of them or a multiple of them. Okay. So this And we can write it a few ways. Another way of writing this is that root lambda is equal to n pi over L. Another way is lambda squared, or lambda is n pi over L quantity squared. But the takeaway is that, well, for lambda greater than 0, does that possibly work? The answer is yes, it works. This is what lambda should be. And then phi should just be sine of root lambda x, or a sine of n pi over L x. Okay. So what we've done here is we've said, well, looking at this case lambda positive, our solutions have to look like this. And we figured out what lambda should be and what phi should be in particular. Okay. So in summary, right, so for lambda greater than 0, our eigenfunctions are these, where root lambda satisfies this, or equivalently that. Okay. And then another way of writing this is phi of x is some constant times sine of n pi over L x. Okay. And so what this note is saying is that, right, in this analysis, we haven't said anything about what this constant C1 is. So a priori, C1 could be anything. Okay. And what we'll see in a bit is, well, right, how do we figure out what this constant might be? That's where the initial condition will come in. The initial condition will tell us what that constant should be. Okay. Great. So that's lambda positive. So that's one of 3 cases. So let's look at the other 2. So if lambda is negative, we know our solutions take this form, because again, we're solving some second order constant coefficient ODE. Okay. So then the question is, right, what possibilities are there for negative lambda, and likewise for C1 and C2? Okay. And again, for those, we use the boundary conditions. So if phi of 0 is equal to 0, right, plug in 0 there, 0 there, e to the 0 is equal to 1. So this is going to go to 1, this is going to go to 1. And we're left with this equation right here. And then rearrange things. You can say, well, in this case, C2, whatever that constant C2 is, has to be minus C1 for this to work. Okay, so let's use the second boundary condition and see what we can get. So second boundary condition is, right, the value at x equals L is equal to 0. So phi of L is equal to 0. Plug in L, right? You can get L there. Use this thing, this condition, to plug in for C2. So what we're going to end up with is this expression right here, right, where C1, so C1 times this difference is equal to 0. Great. So what does this give us? Well, either C1 is equal to 0, or this expression right here is equal to 0. Well, if C1 is equal to 0, then we know that C2 is equal to C1. So if C1 is 0, then C2 is also 0. So then this is 0, this is 0. So our solution is just the trivial solution, phi is equal to 0, right? And those, again, are the solutions we want to avoid. We don't want to, we're not going to try to make sense of in these contexts. So C1 we cannot have C1 equal to 0. So that tells us that this expression right here has to be equal to 0. So we can write it like this. Another way to write it is, so this is equivalent to, right, if you multiply by e to the root minus lambda L on each side, you're going to add them, and so that's going to turn to 0. So this is equivalent to e to the 2 root minus lambda L is equal to e to the 0. However you want to deal with it, what you end up getting is some sort of equation that'll say, well, here, so let's write it like this. So 2 root minus lambda L is equal to 0, which is equivalent to what's written here. So 2 is non-zero. L is going to be non-zero, right? Because it's our length of the rod. We want that to be, right, non-zero. We want our one-dimensional rod to have some length. Non-zero, non-zero. So the only other possibility is that this term right here is equal to 0, which implies that lambda must be 0. But already this gives us a contradiction because, right, for this whole analysis, we were saying, well, lambda is strictly less than 0. And if we run with this assumption that lambda is less than 0, we end up concluding that lambda has to equal 0. So there's some contradiction there. And then the takeaway is, well, right, if we assume this possibility, things get weird, so this can't actually work. Okay. Right, so in summary, if this is going to happen, right, our solutions take this form, but we just saw that, right, lambda has to be 0 for this to work. Coming from our boundary conditions, contradicting that. So, right, a solution in general, a solution like this won't work for our boundary conditions. Okay, and so the conclusion that we'll make for our, kind of the larger problem that we're solving is that, well, lambda less than 0 is not a viable eigenvalue, right? And then the corresponding phi aren't actually eigenfunctions. Okay. Okay, so far we've seen lambda greater than 0 gives us viable lambda and gives us a viable phi. Lambda less than 0 does not give us a viable phi and hence is not a viable lambda. The third case we're going to look at is, well, what happens when lambda is equal to 0? Okay, so if lambda is equal to 0, our solutions are going to take this form. And I guess I've switched the constants, but whatever. For lambda equals 0, solutions are going to take this form. And so again, plug into the boundary conditions, see what we can get. First boundary condition says phi of 0 is equal to 0. Plug in a 0 there, you're going to get a 0 there. So C1 times 0 plus C2 is equal to 0, tells us that C2 is equal to 0. So in this function phi, we don't actually see a C2, right? It's just C1. Okay, and so plug in L here, right? Phi of L is equal to 0, tells us C1 times L is equal to 0. L is non-zero. So this is non-zero. The only possibility is that C1 is equal to 0. Okay, but now we have C1 and C2 are both 0, so that phi is equal to 0. Okay, so if we consider the problem for lambda equal to 0, the only possible eigenvalue or eigenfunctions are the trivial solutions. Phi is equal to 0. And those are the solutions that we're not interested in. Okay, and so we're going to say, well, in this case, lambda equals 0 is not a viable eigenvalue. Okay, so in summary, the only possibility for the spatial piece, right, the only possible solutions for this boundary value problem ODE are phi of x is sine of root lambda x, and we're ignoring the constant because it doesn't actually matter, kind of for qualitatively seeing what the solutions are. So yeah, the solutions are phi of x is equal to sine of root lambda x, where root lambda satisfies this, or equivalently, lambda is equal to that. Okay. And so that's the eigenvalue problem solved. This is the solution. These are the eigenvalues and eigenfunctions for this problem. Okay. Cool. So we've solved the time piece. We've solved the spatial piece, right? And recall that the main motivation or kind of where these problems came from, was we were interested in product solutions to the heat equation. Okay? And so now the question is, right, well, how do we put these things together? What does it look like? And so that's what we're going to talk about next, right? So product solutions, recall, we're looking for u of xt is equal to phi of x and g of t. Okay. So looking for these solutions, we said, well, the time piece looks like this. The spatial piece looks like this. And then lambda, this separation constant, lambda looks like this. So actually taking lambda and plugging it in everywhere we see it, we get that g of t is equal to some constant times e to the minus k n pi over l squared t. And then phi of x, it's going to be some constant times sine of n pi over l x. Okay. So plugging each of these things into our product solution, we conclude that, right, our product solution is going to be some constant, which I'm calling b, times sine of n pi over lx times e to the minus k n pi over l quantity squared t. And so note that, right, we have a solution for every possible integer n. When we solve this eigenvalue problem, right, in here, we didn't get any information about what n could be. So a priori, any n could work. Okay. But yeah, and so presumably in specific problems, they'll tell us what n should be. So let's look at an example of that. So consider the following problem, right? Heat equation, 0 temperature boundary conditions. And now our initial condition, u of x comma 0, that's going to be this function 4 times sine of 3 pi over l x. Great. So the only difference between kind of what we see here and what we saw before, leading to, you know, constructing these product solutions, is now we're specifying what f of x actually is. And so the question is, can we match this template solution to the given initial condition? Okay. So as I mentioned, right, here's our template solution. Okay. If we plug in t is equal to 0, right? So this is unaffected, this is unaffected. Oh. T is going to go to 0. So e to the minus k n pi over l squared t, this is going to go to 1. So the value of our solution at t is equal to 0 is going to be b times sine of whatever times e to the whatever. This is just 1. And so then we're left with b of sine of n pi over l x. Okay. But in the problem, we were told that u of x comma 0 is equal to 4 times sine of 3 pi over l x. Okay. So just comparing these two pieces right here, it's reasonable to say, well, what should be this constant in front be? The constant should be 4, which n works, while n is equal to 3 works. Okay, so for our general product solution to work for this specific initial condition, we need b is equal to 4 and n is equal to 3, so that our solution to this heat equation looks like this. Okay. So nothing super fancy, just saying, hey, we know what our solution looks like. Our initial condition looks really close to this. Let's just say, you know, kind of use the best guess, most reasonable guess, and get these constants. Okay, so let's look at a slightly different problem. So same PDE, same boundary conditions. But now we're saying, well, now the initial condition is going to be a sum of two of these relatively simple looking functions, right? This one is the same one from a second ago. This term is now added on and is slightly new. Well, so how are we going to solve this? So, right, the observation is, well, if we didn't have this piece right here, and we just had this piece, okay, then our solution will probably look like, so coming from here, u of x comma t would be, so the constant would probably be 7, or will be 7, and then sine of 8 pi over Lx, okay? So n is equal to 8. And so then if we incorporate the time dependent piece, we're going to get E times minus K 8 pi over L squared T. So this thing right here works if we just had this initial condition. And so actually, yeah, so then let me write. So here, the piece that works here is going to be, again, 4 sine of 3 pi over Lx E minus K 3 pi over L squared T. So this solves everything if we just have this and not that. Okay, so now the question is, well, can we take these two solutions kind of to the individual initial conditions and then combine them in some way to solve the problem where the initial condition is a sum of kind of these two initial conditions, right? And so the observation is, well, sure, let's try it. If you take this plus this, right, plug it in here, okay, really what we're working with right here is kind of the heat operator, which we saw was linear, right? And so if you add two solutions to this linear homogeneous PDE, right, you're going to get a new solution to that linear homogeneous PDE, okay? So if we add this to this and then plug them in here, they're going to solve this. That sum is going to solve this, okay? And we could say, okay, well, what about the boundary conditions? If we add this to this, do they solve the boundary conditions? Well, to check, we're going to plug in x equals 0. Plug in x equals 0 here. This whole thing becomes 0. Likewise, this whole thing becomes 0. So we're doing 0 plus 0 is equal to 0. So yes, this plus this satisfies this boundary condition. Likewise, if you plug in x equals L to there and then to there, this becomes 0, this becomes 0. So we have 0 plus 0 is 0. And yes, this sum satisfies this boundary condition as well. And of course, plug in t is equal to 0. This is going to go to 1. This is going to go to 1. So you're going to be left with this sine term plus this sine term, which is exactly that. Okay, so it's a long way of saying, right, we have a sum of these template, right, product solutions. We add them together. That sum satisfies all of this stuff. And if you plug in t equals 0, t is equal to 0, we see that the sum also satisfies this initial condition. So the solution to this entire, right, slightly different problem is going to be exactly this expression right here, right, that we had written out a second ago, because solves PDE, satisfies boundary conditions, satisfies the initial condition. Okay, so what this is suggesting is that, well, right, what if our initial conditions aren't these super nice, right, sum of basic sine functions? How do we start dealing with initial conditions that we might see in the wild. Okay, so motivated by this problem, right, we're going to hope that in general, we can construct solutions by just adding up a bunch of these basic product solutions. Okay, and so of course, if we're adding up a bunch of these right product solutions, each of these product solutions had a constant that depended on n. So we're going to specify that the constant that appears right here, yes, depends on n, a different constant for each of these different building blocks. Yeah. But we're going to look for, we're going to look slightly more generally, and we're going to look for these general linear combinations of these product solutions. Okay. And so it's not hard to check, right? Plug this in to the heat equation, right? It solves the PDE. Plug in the boundary conditions, right? So x equals 0 and x equals L. This whole thing is going to be 0 at both of those places. And so then the remaining question is, when does this satisfy an initial condition, f of x equals u of x comma 0, which is going to be the sum of b sub n times sine of n pi over Lx. Okay. So a lot of what the rest of this course is going to be kind of looking at this question. When can an initial condition f of x be represented as a sum of sine functions? And if it can be represented as a sum of sine functions, how do we compute what these coefficients have to be? Okay. And so we're actually going to take it so as I said, we're asking which functions f can be represented in this way. These things are called Fourier series, after the mathematician, physicist, whatever, Fourier. And yeah, so a lot of kind of the more mathematical aspects are things that we'll be addressing in future chapters. So, okay, but at least for this chapter, we'll be able to use these expansions, right? Assume that they work, and actually get solutions to some of these problems. Okay, but yeah, and so we're actually going to take it up a notch, and instead of just taking these finite linear combinations, we're going to be looking at infinite linear combinations. Okay, and so because we're adding infinitely many of these terms, already the question of convergence should be popping up, right? Does this infinite series, which itself is a function of two variables, does this infinite series actually converge? Okay. And likewise, right, which initial conditions can be written in terms of this infinite series? So those kind of more theoretical aspects are, again, things that we'll look at in the next chapter. But what we'll be doing in the rest of this chapter is kind of taking on faith that this expansion works. We'll show in a second how we actually compute what these b sub n are. And then we'll be able to construct our solutions. Okay. Okay, so then the question is, sure, if this works, how do we figure out what these b sub n are? And so that's going to get back to this kind of very geometric way of thinking about kind of vectors, especially where kind of the vectors of interest are functions themselves, right? And so what we're going to be talking about is this notion of orthogonality, okay? But in particular, we're going to be looking at orthogonality of sine functions, because kind of our basis vectors are going to be functions of the form, right? So the signs that we care about are of the form for n. I mean, you can include n equal to 0, but it's just going to give you the 0 vector. Okay, and so maybe in a very hand-wavy sense, essentially what we're going to be saying is this collection of functions for n greater than 0, these form a nice basis of vectors for really any of the function spaces that that we'd care about. Okay, and so for these functions to form a nice basis, we want them to be orthogonal to one another in a sense. You might also want to normalize the vectors. They have length or size or norm 1. But for us, we're not going to worry too much about that. Okay. Okay, so question is, right, so if we know, suppose some function can be represented as this infinite sum. We have some coefficients b sub n times the sine of n pi over lx. Okay. The question is, how do we compute these b sub n? And so title of the slide is Fourier coefficients. These things, these b sub n, these are what we're calling Fourier coefficients. Right, they're coefficients of a Fourier series. Okay, so how do we compute them? Well, we're actually going to use this interesting kind of integral involving sines, where if you take this sine function, multiply by this sine function, right? So the difference is one is n, the other is m. If you take a product of these two sine functions, then the integral is either going to be 0 if n and m are different, or it's going to be L over 2. Okay. This thing right here, this is orthogonality of sines. So this integral is how we're kind of comparing or measuring these sine vectors or functions kind of against one another. And so the claim is that if you have different ones, if n and m are different, then these two vectors are going to be orthogonal because this quantity is equal to 0. Likewise, if these are the same, then that quantity is going to be L over 2. And so then this L over 2 is going to be kind of the size of the vector that is sine of m pi over Lx. Okay. But for actually computing these coefficients, we don't really need to worry about the geometric picture of kind of orthogonality and what we're measuring here. We can kind of ignore that and just use this kind of in a very explicit way to isolate these b sub n. Okay. And so that's what we're going to look at next. Okay, so starting point is, right, so we're assuming that we have this decomposition. We're assuming that we can write f of x as an infinite linear combination of some coefficients times some sine functions. What we're going to do is we're going to multiply both sides of this equality by sine of m pi over L x. Okay, and moreover, we're going to distribute this sine of m pi over Lx kind of over this infinite summation and assume that that's a valid operation. Okay. So multiply both sides by sine of m pi over Lx, distribute that sine of m pi over Lx across that infinite summation. We end up with this expression. Okay. And note that over here, summation is over n. And so this m is constant for each of these terms. Okay, and so now what we're going to do is we're going to integrate both sides from 0 to L with respect to x. So this is kind of starting to get at, here's where that integral trick is coming into play. So integrate both sides with respect to x from 0 to L. Okay. On the left-hand side, we get this integral, which without knowing what f of x is, there's not a whole lot we can do. This is pretty much the final form for the left-hand side. On the right-hand side, right, well, all we're doing is integrating from 0 to L dx. But what we're going to do now is we're actually going to distribute this integral over this summation. Okay. Now, if we had a finite summation, there's no issue with kind of distributing the integral, right? Integration is a linear operation. As soon as you're summing over an infinite amount of things, the validity of that distribution can be in question. We're going to assume it works out. Okay, so if we distribute that summation or this integral over the summation, and keep in mind that this b sub n is constant. Okay, so this constant b sub n, we can pull it out of the integration. What we're going to end up with is the same integral on the left-hand side is equal to this infinite sum of this constant b sub n times this integral. Okay, so those are the operations, right? This integral right here. So keep in mind that this is exactly, right, the identity we had right here. So actually what I can do is copy this, paste it here, right, and say, well, let's take this identity and see what it looks like here. Right, so the observation is, well, in here, we're summing up from n equals 1 up to infinity. So what does this thing over here actually look like? Well, let's write out a few of the terms. So we have b sub 1 integral 0 to 1 or 0 to L of sine of 1 times pi over Lx, sine of m pi over Lx dx, plus b2 times the integral from 0 to L sine of 2 pi over Lx, sine of m pi over Lx dx, plus dot, dot, dot. Okay, so the point is, because we're summing up over kind of these infinitely many terms, n equals 1 up to infinity, if we actually write out what we get, what we're going to see is m is fixed here. So eventually, we're going to get to a term where n, the thing we're summing over, is equal to m. Okay? And when that happens, this integral for n is equal to m, this integral right here, or kind of wherever it appears, is going to equal L over 2. Okay? But as soon as you find where n is equal to m in the summation, right, the next term, m and n are going to be different. And so then that next integral is going to be 0. And then the one after that's going to be 0, etc. Okay, so the conclusion is, right, because of this identity, only one of these terms in this infinite summation is actually going to be non-zero. Okay. Okay. Isn't it? Okay. So yeah, so the only non-zero term is going to occur when n is equal to m. Right. So in that case, right, left-hand side unchanged. This in this summation, the only non-zero term is going to be when n is equal to m. So then technically down here, this should read b sub m, and then sine of m pi over Lx. Okay, because again, right, we're summing over every possible n. When n and them are different, we get a 0. So we'll get like 0 plus 0 plus 0 plus this thing, then plus 0 plus 0 all the way off to infinity. Okay. And we know what this integral is, right? This integral is exactly L over 2. And so in this way, we've figured out what this constant b sub m is. right? So dividing by L over 2, which is the same as multiplying by 2 over L. This tells us that B sub m is equal to 2 over L integral from 0 to L sine m pi over Lx f of x dx. And so that's exactly what the summary is, right? So if we're assuming that we have a decomposition like this, f of x is equal to this infinite summation of sine terms, then these coefficients must be exactly equal to these integrals. Okay, great. So, right, what we have is, if we have this decomposition, we know how to compute these coefficients, right? And these decompositions, these were appearing as solutions to the heat equation. So now that what this is suggesting is, well, maybe now we know how to solve the heat equation. We know exactly how to, right, construct a solution, right, up to some coefficients, and then figure out what coefficients we need to match that solution to the initial condition. Okay. Okay, so before actually solving something, what I'll say briefly is, right, how this notion of orthogonality comes up. Okay. So if we have two vectors, so v1 is this vector in three-dimensional space, v2 is this vector in three-dimensional space. We have what we'll call, or we've called, like an inner product or a dot product. Okay. Sometimes it's written as this with these angled brackets. Sometimes it's written with a dot. Okay. But kind of the mathematical operation is, well, whenever you see either of these, you interpret that as multiplying the vectors together component by component and then summing that up. And so then we say that, well, vectors are orthogonal if this inner product, this dot product, is equal to 0. And I mean, another way to interpret this is, so let me write it like this. V1 dotted with V2. You can also express this as the magnitude of V1 times the magnitude of V2 times sine of the angle between the vectors V1 and V2. I think this should actually be cosine. Yeah, this should be cosine. Okay. And so then this gives you a way to compare kind of this dot product defined in this way to the magnitude of the vectors and something like the angle between them. Right, and so if the angle between the vectors is 90 degrees or pi over 2, cosine of pi over 2 is 0, and so then v1 dot v2 is equal to 0. Okay, so this is kind of geometrically why we call this kind of this orthogonality condition. Okay, great. So what we do for functions is we say, well, we're going to do the same thing. We're going to say two functions are orthogonal if some expression like this holds. Okay, and so then the question is, what is kind of this thing, or what is this sum of kind of values of the vector? What is the corresponding thing for functions? So for functions, if they're defined on the same interval, what we do is we define kind of this dot product or this inner product to be the integral of the two functions multiplied together, integrate from 0 to L, bounds of the functions, and that's our inner product. So So F1, F2, we'll say they're orthogonal if, right, their inner product, F1 and F2 is equal to 0, which is the same as saying this integral, 0 to L, of F1 of X, F2 of X, dx is equal to 0. Okay. And so there are a few ways you can start to interpret this geometrically. But using this kind of inner product or dot product, right, kind of that integral trick that we saw before, that identity manifests as saying these functions sign are orthogonal for n and m different. Okay. But anyways, so kind of this linear algebra perspective isn't really necessary to actually computing and constructing solutions to the heat equation. But it is kind of what's going on under the hood. Okay, cool, great. So let's actually see kind of an example, right? That's maybe a little more interesting than having an initial condition that's a sine function. Okay, so what we're going to do, consider a rod of length L with initial temperature 100 degrees. Okay, so that might look something like this, where this temperature, we're going to say that's 0 and then 100's right there. So the initial condition is something like this. Okay. X equals 0, X equals L. Suppose both ends of the rod are kept at 0 degrees. Okay. How does the temperature in the rod evolve? And so mathematically, right, we're looking at the heat equation, right? So evolution of heat. Both ends of the rod are kept at 0 degrees. That's going to give us these boundary conditions. Initial temperature is 100 degrees, tells us that the initial condition is 100. Okay. Okay, and so what we want to know is how heat evolves. So what we want to do is find the function u that works here. And so, right, one thing to note, technically the initial condition, right, u of x comma 0 is equal to 100. Technically, this initial condition doesn't satisfy the boundary conditions. That's part of the mathematical reason why we specify this initial condition only holds on the interior, so not exactly at the endpoints. In practice, it doesn't really matter because we're integrating, and generally integration doesn't care if you change the value at a single point. But anyways. Okay, so let's use the machinery we've developed. So everything we've developed so far has said solution should look like this. Okay. These are the solutions we're looking for. And we've already verified that these solutions satisfy this and satisfy this. Okay. So the only thing that we still need to do is show that, right, this solution right here satisfies this initial condition. Okay. Or, you know, stated kind of another way, right? So plug in t is equal to 0, t is equal to 0, this thing is 1. So what we end up with is saying is kind of u of x comma 0, which is equal to 100, that has to equal this thing. Okay, but we saw a second ago exactly how to compute these coefficients b sub n so that this decomposition works. The b sub n are computed using the formula b sub n is equal to, right, 2 over L times the integral from 0 to L of f of x, the initial condition, times sine of n pi over L x dx. Okay. So carrying out that integration, right? Antiderivative of sine of n pi over Lx is minus L over n pi cosine of n pi over Lx. You can check this by taking the derivative of this. You should end up with that. This 100 has been pulled out to get 200 over L. Bounds of integration are 0 and L, so that's where those bounds come in. Okay. And so plug in the bounds, right? Okay, so let's see what we've done here. So this L is canceled with that L. Let's see. So plug in. Yeah, okay, so written out. So this is, so this is going to be 200 over L times minus L over n pi cosine of n pi minus, and then this whole thing, plug in x equals 0. Cosine of 0 is 1. So it's going to be minus L, so minus L over n pi. Okay. Minuses cancel, pull out an L over n pi. So then we're going to get, right, so that these L's are going to cancel with that. These n pi's are going to come out here. So we're going to be left with a +1 from this, and then a minus cosine n pi from this. And so that's exactly what we have here. Okay. And so then, so sure, if you want to leave it like this, it's fine. If you want to simplify it a little bit and say, well, when n is even, so for example, n is equal to 0, right? Cosine of 0 is equal to 1. So n is equal to 0 means that this term is 0. So then this whole thing is 0. When n is equal to 2, this is equal to 1 again, etc. When n is odd, so let me write it out here. So this is because cosine of n pi is equal to 1 if n is even, -1 if n is odd. Right, so whenever this is -1, minus -1 becomes +1, and we pick up a 2, so we pick up a 400 over n pi. If you want to simplify it like this, that's fine. If you want to keep it like this, that's fine as well. But the point is, we know what these coefficients b sub n are. These are the coefficients. So our solution looks like this. If you don't want to do that simplification, you can also keep it as sum from n equals 1 up to infinity of 200 over n pi, 1 minus cosine n pi, sine of n pi over Lx, e to the minus k, n pi over L squared t. Either form is fine. But yeah, this is our solution. This whole thing solves the heat equation that we posed, where initial temperature is a constant 100, value at the endpoints is 0. Otherwise, it evolves like heat does. Cool. Yeah, and so kind of what I was mentioning before, at t equal to 0, it's technically not, it's discontinuous, say. It's 100 on the interior, 0 at the boundary points. So a better way to say it is the solution is discontinuous at x equals 0 and x equals L. Turns out it's not really a problem. The other observation is that this term goes to 0, right, as t goes to infinity. Especially if this whole thing, if this is really large, then the rate that this goes to 0 is a lot faster. Okay, so on the baseline that says, well, all of these terms are going to 0 as t goes to infinity. So then our solution should be going to 0. If we want crude approximations of kind of what u of x comma t is doing, well, right, these terms go to 0 faster for larger n, so we can say, well, let's take a smaller n, say n equals 1, plug in n equals 1, just take that term and use that as an approximation for what's happening. Okay, so what that would look like is something like this. So then, so this would be at t equals 0. So plugging in n equals 1, we're going to get effectively sine of pi over Lx, which is going to behave like sine between 0 and pi. So we're going to get something like this. This is going to be t small. And then as t starts to increase, we're still going to get this basic profile of sine, but then this is going to be pushing sine to 0. And so then this is going to be this approximation for t larger. So this picture right here corresponds to this approximation. Okay, and so of course it's not really how it behaves. You'd expect there to be less of a sharp, I don't know, discrepancy between these corners and kind of the sine solution, but as a rough approximation, this is giving us a sense of what this evolution of heat looks like. Okay, cool. So that was a lot. What is a quick summary of everything that we've done? So if we're given a problem like this, okay, where we have heat equation, 0 boundary conditions, right? It's important that the value of the solution is 0 at the endpoints. And we have some initial condition. Okay. How do we go about solving this? Well, first, make sure we have a linear and homogeneous PDE, linear and homogeneous boundary conditions. That's what this is. Good to go there. We're going to temporarily ignore this initial condition. We're going to separate variables, right? So the separate variables, this would say u is equal to phi times g. Okay, and then figure out what phi and g are. We're going to determine the separation constants. Is the eigenvalues for this boundary value problem. And so this 4 is saying solve for phi, and then figure out what lambda work, which lambdas work. Solve for the time piece, right? Solve for g. That's going to give you your product solutions. Apply the principle of superposition to add all these product solutions together and get this most general solution. Attempt to satisfy the initial condition. This is, right, this one was solve the B sub n, or compute the B sub n. I guess technically 7 and 8 were compute B sub n. Okay. Okay, so this is a summary that's in the book. In practice, what do? Well, practice, if we know that we're working with all of this problem right here, what do we do in practice? Take this, plug in our initial condition to get this, and then solve the B sub n using this formula where here you had f of x, your initial condition. And so once you've solved these coefficients, plug these back in there, this will be your solution to the given problem. Okay. So this is a lot, but this is also kind of the main tool that we'll be using for the rest of this course, and kind of variants of this tool as well. Yeah.